All right, good morning, guys. Sorry for that little delay. I had to change a diaper real quick before you come in here and get started. But today is going to be another fun day for us because today we are continuing in our little exploration of linear algebra. Specifically, we're going to start learning about the algebra of matrices today. So last time we introduced matrices as a concept. And we worked with them doing some row operations in order to solve systems of linear equations. And that's definitely like genesis for this topic. So matrices sort of came about because people just realized they could solve systems of equations without writing the variables. You just write the numbers instead. It turns out that some very clever folks realized that these matrices can be thought of as more than just placekeepers for the variables. It's more than just a time-saving trick. They need not be, and for a long time, people did just think of matrices as these arrays of coefficients. But what mathematicians like to do, and given time, what they will do is abstract. So once you have an object that you are familiar with, you start asking, well, what else can I do with this? And the beauty of matrices is that if you restrict your attention to the kind of natural operations for linear algebra, meaning like multiplication by constants, addition, that sort of thing, then you can start to think of the matrices themselves as variables, which means you can construct matrix equations. And those matrix equations can be solved a lot of different ways. And the solution to a matrix equation will, in one fell swoop, yield a solution to the corresponding linear system. So today, what we're going to do is, I'll remind you a little bit, what matrices are and how to write down the matrix for a system. But then we're going to talk about the algebra of matrices a little bit. So let me get a nice black pen. We'll turn on screen share. Got to get that .cam software up. All right, here we go. You can tell this is a little bit offset. That's so frustrating. All right. So here we go. So this is MAC1140 section 0R1, which is pre-calc. And the date today is the 29th of November, 2021. Today, we're going to begin talking about the algebra of matrices. And as we dive in here, I'm going to just kind of remind you how to write down the corresponding matrix for a system and the row operations that we want to do to solve a system. So I'll just say recall. This is section 10.4. Recall that given a system of linear equations, we can write a matrix. So for example, oh, sorry, kitty, get the hell out of here. I love you, kitty. No, I know. Life is hard. Life is hard. For example, I could take the system 4x plus 8y minus 4z equals 4. 3x plus 8y plus 5z equals negative 11, and negative 2x plus y plus 12z equals negative 17. I can take this system and rewrite it as the so-called augmented coefficient matrix. Which will be a 3x4 matrix whose first row is just the coefficients here and then this. So 4, 8, negative 4, 4. The second row would be the numbers from the second equation, 3, 8, 5, negative 11. And whose third row is the numbers or coefficients from the third equation, negative 2, 1, 12, negative 17. And I like to put this little vertical dividing line in here to remind me what is what. Namely, the stuff to the left of that line, these are the coefficients of the variables. So just this stuff is called the regular coefficient matrix. And all of this, with the right-hand side included, is called the augmented coefficient matrix. And we saw last Wednesday that you can solve this linear system by running row operations on the matrix. The system can be solved by using row operations to, the term is reduce the matrix to triangular form. Then back substitute. I know it's been a long holiday weekend, so that's why I'm taking the time to remind you of these facts. It is important that you have practiced this procedure where you rewrite your system as a matrix and then go through the row reduction process. I remember triangular form means these and these are 0. Everything beneath this main diagonal here is 0. In this case, a bunch of row operations would yield. I'm just going to write row ops. In this case, after we do a bunch of row operations, what we would arrive at is the matrix. What we could arrive at if we put this all the way into this form this. Now we said on Wednesday of last week that we would be happy just having these guys down here be 0. So we didn't necessarily require that these diagonal entries be 1, and we didn't necessarily require that these entries up here be 0 either. But if you have this totally reduced so that your first column is just 1, 0, 0, your second column is 0, 1, 0, and your third column is 0, 0, 1, I would like you to observe that this is now equivalent to the system x plus 0y plus 0z equals -3. 0x plus 1y plus 0z equals 1. And 0x plus 0y plus 1z equals -2. i.e., x equals -3, y equals 1, and z equals -2. So the solution is the ordered triple, -3, 1, -2. When we did these problems in class, we didn't make all these diagonals 1, and we didn't worry about making these upper entries here 0. And when you solve these systems by row reducing a matrix, you don't need to do that. But I just want to point out how nice it is if you have this coefficient matrix in this form, because that means x is -3. This means y is 1. And this means z is -2. If you continue using row operations after getting your zeros here and here to get zeros here and here and ones along the diagonal, then this will just be your solution. Whether it's worthwhile to spend the extra time doing those row operations versus doing what we did last week, which is just, you take that last equation, maybe it says 3z equals 6 or something, -6, solve that and then back substitute, is a matter of taste. And I would say if you're doing the row operations by hand, generally it's not worthwhile.
I have a question.
Sure.
Is it always in a diagonal line? It's always 1?
Maybe I want to make sure I understand. Are you asking, is this diagonal always going to be ones?
Yes.
It need not be, right? Like the examples we were doing last Wednesday, we didn't get ones here. All we cared about was having zeros here and here. Because, imagine this last line, this last row, instead of being 0, 0, 1, -2, it could be 0, 0, 3, -6. And then this last equation would be 3z equals -6. And you can still solve that for z, just dividing both sides by 3 when you get z equals -2. So in general, what we needed, this triangular form, let me sketch in what we called our triangular form. Different color maybe. Triangular form, what we required here was something like 2, 0, 1, 3, 0, 3, -1, 5, and then 0, 2, 4, something like this. We would have said is in upper triangular form or triangular form. So you could just take something like this, right? And then this last equation, this last row would tell you -2z equals 4. So z is -2. You would plug that into this guy, which says 3y minus z equals 5. And that would let you solve for y. And then you would take both z and y and plug them in here to solve for x. So you can solve the system from this form where you don't necessarily have ones here and you don't necessarily have zeros here. All we really need are zeros here and here. Everywhere below this main diagonal, we need zeros. But the point of what I'm showing you down here is that if you have ones along the diagonal and zeros everywhere else, then boom, this is your solution. You don't have to do anything else. You just say, okay, -3, 1, 2, -3, 1, 2. Because each of these rows represents an equation that just says, for example, here, x equals -3, y equals 1, and z equals -2. So if you're able to get your matrix into this form, where the main diagonal is all ones and everything else is zeros, then the right-hand side here is going to be your solution. And that's a very nice observation. It's not necessary, but a matrix in the form that we see up here matrix in this form is said to be fully row reduced, or it's called reduced row echelon form, which is just a fancy way of saying you've done everything you can possibly do, right? You've done all the row operations you could possibly hope to do, because now the first equation just tells you x, the second equation just tells you y, and the third equation just tells you z. In other words, you don't need to do any back substitution. And that procedure we described for row reducing matrices, you can continue using those same rules to get here. Remember what we did. First, we cleared out the things down here. We made those zeros. And you could make this a 1 just by dividing through the first row by whatever constant you had here. If this was a 3, you could divide everything by 3. After we made these zeros, we wanted to make this a 0, and we would generally use this row as our tool to do that. And if you wanted, you could, having made this 0, then divide through row 2 by whatever you need to get a 1 here. Then you'll have something like 0, 0, 3, -6. You can divide through to get a 1 here, and then work your way back up, making these zeros and making this 0 in the same way that we were making these guys 0. I'll show you some examples as we go through that. But before we get there, we'll be talking about that when we get to talking about inverting matrices. Before we get there, I need to introduce the algebra of matrices a little bit. So this is just kind of our recap and a little bit looking forward, that we can do more row operations to put something in this fully reduced form or reduced row echelon form. When I say we're going to learn the algebra of matrices, I mean, I'm going to tell you how to add two matrices, how to multiply two matrices, that sort of stuff. Before we do that, I want to tell you what it means for two matrices to be equal. If capital A and capital B are matrices, then A equals B means two things. First, A and B are the same size, right? Like both 3 by 3 or both 5 by 4, right? Whatever. Same number of rows, same number of columns. So in order for two matrices to be equal, they have to have the same number of rows and they have to have the same number of columns, have to have the same dimension. The other thing is that the entries have to be equal to each other. And in that notation, which we introduced on Wednesday of last week, where the entries of A are Aij, and the entries of B are Bij, this would mean that Aij is equal to Bij for all I and j. So this is what it means for two matrices to be equal. They're the same size and the entries match up. In other words, you set the matrices down on top of each other and everything lines up. Okay, so for example, if I want to find the constants little a, little b, little c, and little d, if the matrix A, B, C, D is going to be equal to the matrix 1, 3, -5, 2. Well, these are both 2 by 2 matrices. They both have 2 rows and 2 columns. So that first condition is met. And then what I need is all the entries in A to be equal to the corresponding entries in B. Okay, well, this means that A had better be 1, right? This entry has to match this entry. B had better be 3. C had better be -5. And D had better be 2. Right? Not as complicated as this definition makes it sound. Two matrices are equal if they're the same size and they have the same entries. That's it. All right. Your basic algebra for matrices, the basic operations, addition, subtraction, and scalar multiplication, are all defined the way you would think. Meaning if I want to add two matrices, I'm going to add their entries. If I want to subtract two matrices, I'm going to subtract their entries. And if I want to multiply a matrix by a number, I multiply every entry by that number. Let me do this on a fresh page. Remember back when we talked about transformations of graphs, I referred to multiplying the function by a number as a scaling. That terminology comes from this. So a scalar is just a number, right? A scalar is a constant. It's just another term for a constant. So let's let the matrix A be the matrix whose entries are A, I, J. And this is an m by n matrix. And let capital B be the matrix whose entries are B, I, J, also be an m by n matrix. Then A plus B is going to be a new m by n matrix whose ith entry is the ith entry of A plus the ith entry of B. I'll do examples here in a minute, but what that means is that you just add up the entries. You take the entry in row 1, column 1 of A and add that to the entry of row 1, column 1 of B. And you do that everywhere. The new matrix A minus B is also an m by n matrix, same as the common size of A and B. And to find his entries, you just subtract the entries of B from the entries of A. And the scalar product, C times A, where C is just a constant, will be another m by n matrix whose entries are the entries of A, just all multiplied by that number C. I'm going to annotate each of these with some words that make them a little easier to understand. This means you just add the entries. This means that you just subtract the entries. And then this last thing, to multiply a matrix by a number, you multiply all the entries by that number. So some examples. Or maybe before we even say that, to add two matrices together, to subtract two matrices from each other, they have to be the same size. Right? These are both m by n matrices. So in order to do either of these operations, just like in order for two matrices to be equal, they have to have the same number of rows and the same number of columns. So I'm going to give us some specific matrices here, and we're going to do some computation. Let's let A be the matrix 2, -3, 0, 5, 7, -1/2. Let's let B be the matrix 1, 0, -3, 1, and 2, 2. So A and B are both 3 by 2 matrices. They both have 3 rows and 2 columns. Let's make the matrix C something else. 7, -3, 0, 0, 1, 5. And the matrix D will also be a 2 by 3, 6, 0, -6, 8, 1, 9. And I want to find, where possible, the following things. A plus B, C minus D, C plus A, and 5A. Right, so I have here 4 matrices, A, B, C, and D, and I want to add A and B. I want to subtract C and D. I want to add C and A, and I want to multiply the matrix A by the number 5. Let's find A plus B first. We write this out. This is 2, -3, 0, 5, 7, -1/2. Plus 1, 0, -3, 1, 2, 2. So here, A and B are both 3 by 2 matrices. We've got 1, 2, 3 rows and 1, 2 columns. 1, 2, 3 rows and 1, 2 columns. So I can add these matrices. They're the same size. And when I add them, what I get is a new matrix who's also a 3 by 2 and whose entries are just the sum of the entries of A and B. So the result here is going to have 3 rows and 2 columns, just like A and B. The 1, 1 entry is going to be 2 plus 1, it's 3. The 1, 2 entry is going to be -3 plus 0, which is -3. The 2, 1 entry is 0 plus -3, which is -3. The 2, 2 entry is 5 plus 1, which is 6. The 3, 1 entry is 7 plus 2, which is 9. And the 3, 2 entry is -1/2 plus +2, which is +3/2. So that's it. You just add up the entries. Questions on how we got this matrix as the sum of A and B? Okay. How about C minus D? Well, here's the matrix C and here's the matrix D. You just write them down. That's 7, -3, 0, 0, 1, 5. Minus D is 6, 0, -6, and then 8, 1, 9. And these are both 2 by 3s. So the result will be another 2 by 3. 2 rows, 3 columns. And the entries here will just be what I get by subtracting from this. So 7 minus 6 is 1. -3 minus 0 is still -3. 0 minus -6 is +6. That's my first row. 0 minus 8 is -8. 1 minus 1 is 0. And 5 minus 9 is -4. So this is the new matrix we get out. It's also a 2 by 3. Any questions on how we got this matrix as our answer? Okay, next we wanted to find C plus A. So C is still the 2 by 3, 7, -3, 0, 0, 1, 5. And I want to add that to the 3 by 2, 2, -3, 0, 5, 7, -1/2. So this is a 2 by 3, 3 by 2. Can I add these two matrices? I could add A and B because they were both 3 by 2s. So every position over here had a buddy over here that I could add to him.
No, you can't. You can't do it.
Very good. Yeah. I could subtract C and D because they were both 2 by 3s. So every guy over here had a guy to subtract over here. But I cannot add C to A because C has like an element in the 1, 3 position A doesn't have anything in the 1, 3 position. It's not that there's a 0 here. There ain't shit here. Also, A has entries in column or in row 3. Like he has a 3, 1 position. C doesn't have a 3, 1 position. This is impossible. Because A and C are different dimensions or different sizes. All right, so I can only add or subtract matrices that are the same size. Got to have the same number of rows and same number of columns. If that's not the case, then you cannot add them, you cannot subtract them. The last thing I wanted to compute here was 5a, which is 5 times the matrix 2, -3, 0, 5, 7, -1/2. This operation is called scalar multiplication, or multiplication by a constant. We can always do this. And according to the rule up there, I should just multiply every entry of the matrix A by the number 5. So I'm going to get out another 3 by 2. This will not change the dimensions of the matrix. And the entries here, I just multiply every number here by 5. So 2 times 5 is 10. -3 times 5 is -15. 0 times 5 is 0. 5 times 5 is 25. 5 times 7 is 35. And 5 times -1/2 is -5/2. These are your basic operations, right? Addition, subtraction, multiplication by a constant, or scalar multiplication. There's something, kind of 2 things ominously missing. I haven't said anything about how to multiply 2 matrices. That can be done, but it is not done the way you would think. You do not just multiply the entries, unfortunately. The other thing I haven't mentioned is how to divide matrices, and that technically cannot be done, but there is something like division for matrices that we will get to in the next section. So let me write down a matrix equation and try to solve it for you. Just a nice simple matrix equation. Let the matrix A be the 2 by 2 matrix, 2, 3, -5, 1. And let the matrix B be 4, -1, 1, 3. And then let's solve the equation, the matrix equation. (2x minus a equals b). For the matrix X. The good news about matrix equations is that those basic properties, the definition of addition, subtraction, scalar multiplication for matrices, means that you can treat everything here like its own variable. You can do regular linear operations like adding, subtracting, and multiplying by a constant, the same way you would if these were just variables representing numbers instead of variables representing matrices. In other words, 2x minus a equals b is equivalent to saying 2x equals b plus a. I can add the matrix A to both sides. And then if I want to get x alone, I can multiply both sides by 1/2. And now I can write this thing down. This is 1/2 times, well, what's the matrix B? The matrix B is 4, -1, 1, 3. Plus the matrix A is 2, 3, -5, 1. If I add those two matrices, 4 plus 2 is 6. -1 plus 3 is 2. 1 plus -5 is -4. And 3 plus 1 is +4. And then if I want to multiply this matrix by 1/2, I'm going to multiply every entry by 1/2. So 6 times 1/2 is 3. 2 times 1/2 is 1. -4 times 1/2 is -2. And 4 times 1/2 is +2. So X is the 2 by 2 matrix, 3, 1, -2, 2. That's it. We just solved our first matrix equation. Some facts about matrix algebra. Addition is commutative. These are things that I think most people would assume or deduce, but bad math teacher if I don't tell you. If A and B are matrices of the same size, and C is a constant, then A plus B is the same as B plus A. Right? Because A plus B, you just add the entries of A to the entries of B. And that's the same if you added the entries of B to the entries of A, because inside those numbers could be added in either order. Addition is also associative, which is a big deal. A plus B, I should say AB and C, capital C. A plus B plus a third matrix, capital C. If you add A and B first, then add C to that, that's the same as if you add A to the sum, capital B plus capital C. Let me make this emphasize that this is a capital. Scalar multiplication also distributes. So let me say, I need another constant here. And little d are constants. So scalar multiplication is nice in all the senses we would want, like little c times little d multiplied together, and then whacking that with capital A. That's the same as taking c times little d times capital A. Then you also have distribution in both possible senses. If you want to multiply the matrix A by the constant little c plus little d, that's the same as little c times A plus little d times A. And also, if you want to multiply little c, the constant, times the matrix A plus B, this distributes as well. This is little c times A plus little c times B. So all the stuff you want to be true is true. And you can verify any of these just by writing down the definition. Like this would be CD times all the entries of A. And this would be D times all the entries of A, then multiply all of those by C. Well, of course, those are the same, right? Each one of these is kind of a duh statement when you think about it. But again, this is something that I'd be a bad math teacher if I didn't tell you these things are true. Really, when we do the stuff like what we were doing up here, I'm relying on these facts. Right? When I say I can solve this by like adding the matrix A to both sides, I'm relying on some of these facts to do that, like commutativity and associativity of addition. But I think it's not something you need to think about terribly hard. Just you can do the stuff you want to do with matrices. The one thing I've avoided very carefully so far is multiplying two matrices. And that's because this is not so intuitive. But we need to talk about it. So to add two matrices, they have to be the same size. To subtract two matrices, they have to be the same size. The rule for multiplication is quite different. If A is an m by n matrix and B is, say, a P by Q matrix, then we can form the product A times B. So I'm going to multiply the matrix A by the matrix B only if the number of columns of A is the same as the number of rows of B. In other words, only if n is equal to P. N, again, is the number of columns of A. And P is the number of rows in B. This is a weird requirement. Also, the resulting matrix will be a, let's see, what is it? An M by Q matrix. So when you multiply two matrices, they don't necessarily need to be the same size. You need the number of columns of the first matrix to match the number of rows of the second matrix. And then the output could be a different size altogether. In the case where these are both square matrices of the same size, both 3 by 3s, both 4 by 4s, whatever, that's the nicest possible case. But that need not be how things go. I'm going to show you how to multiply these. It's not obvious at all. The actual rules are quite strange. And in order to show you how this works, I would like to first show you how to multiply a row by a column, because that's how we do this. Let me get this out of here. So multiplying a row by a column. Oh, sure. So if I take the row, call it just A1, A2, A3, and I want to multiply that by the column, call that just B1, B2, B3. I can do this because this is a 1×3 matrix. And this is a 3×1 matrix. So the number of columns of A, there's 1, 2, 3 columns, is the same as the number of rows of B. There are 1, 2, 3 rows. And of the second number here has to match the first number here. And the result here is going to just be a number, will be a 1×1 matrix. And it would be A1, B1 plus A2, B2 plus A3, B3. So you multiply this and this, you add that to what you get when you multiply this and this, you add that to what you get when you multiply this and this. And in fact, normally we won't write anything here. Sometimes you'll see a big dot because in physics, we call this the dot product. Also sometimes called the scalar product because the output is a scalar or just a number. So for example, if I want to multiply the row 2, -1, 0, 4 by the column 5, 4, -3, 1, I can do that because the number of columns here is 4 and the number of rows here is 4. This is a 4×1, or sorry, this is a 1×4 and this is a 4×1. Those inner numbers match. And what I will get here is just the number 2 times 5 plus -1 times 4 plus 0 times -3 plus 4 times 1, which is 10 minus 4 plus 0 plus 4, which is just 10. The way that we multiply larger matrices is you take a row from the first times a column from the second. That's why the number of columns of A has to equal the number of rows of B, because we need to be able to form each of these little scalar products. So to actually multiply whole matrices.
I have a question real quick.
Sure.
Do they have to, in order to multiply them, I assume this answer is no. Do they have to be the same number of rows to the same number of columns?
Not necessarily. So we
Okay.
just need the number of columns of A to match the number of rows of B. I need the length of a row in A to be the length of a column in B so that I can do this with each row of A and each column of B.
So I couldn't do 3 in a row times 4 columns.
Correct. Yeah,
Okay.
if A has 3 columns, so each row is length 3, and B has 4 rows, so each column has length 4, then we would be in trouble because there would be a mismatch here. We would have like an extra guy here that didn't have a buddy here. So here's what we do. You multiply the rows, multiply larger matrices, A times B. Multiply the rows of A with the columns of B. So if that is, if C is going to be A times B, then the entries of C, the things we call Cij, will be the ith row of A times the jth column of B. That's the rule. So we know how to take a row and multiply by a column. If you want to take two big matrices and multiply them, you take a row from the first and a column from the second, and you multiply them, and that will give you an entry in the new matrix. Let's do an example. First, I'm going to hold here just for a second so you can write this rule down, because this is kind of the intuitive way to think about it, as long as you know how to multiply rows and columns. Believe me, there's a payoff here. This is not just random, weird, made up bullshit, I promise. So I want to, for our first example, multiply to form the product AB, where A is a 2 by 2 matrix, 1, 3, -1, 0, and B is a 2 by 3 matrix, -1, 5, 2, 0, 4, 7. I'll just annotate this here. A is 2 by 2. B is 2 by 3. And if I want to multiply A times B, then I need the number of columns of A, which is 1, 2, to be equal to the number of rows of B, which is also 1, 2. One of the things you may notice here is that AB can be formed, but BA cannot be formed. So the order matters. This means matrix multiplication is not commutative. I'll give you more examples of that in a minute. But here's how we do it. AB, I'll just write it out, is 1, 3, -1, 0 times -1, 5, 2, 0, 4, 7. And what I like to do is write the resulting matrix below. I'm taking a 2 by 2 and I'm multiplying it by a 2 by 3. So the output will be a 2 by 3, whose first entry is going to be the first row of A times the first column of B. So the first row of A times the first column of B, that's 1 times -1 plus 3 times 0. I'll write it. The next entry here, the 1, 2 entry, I get by taking the first row of A and the second column of B. That's going to be 1 times 5 plus 3 times 4. The third entry of row 1 here is going to be the first row of A times the third column of B. That's going to be 1 times 2 plus 3 times 7. That's the first row of the resulting matrix. Like we said, this is going to be a 2 by 3. To get my second row, I take the second row of A and the columns of B. So the 2, 1 position here is going to be the second row of A times the first column of B. That's 1 times, -1 times -1 plus 0 times 0. To get the 2, 2 position, I take the second row of A and the second column of B. That's -1 times 5 plus 0 times 4. And to get the 2, 3 position, I take the second row of A and the third column of B. That's -1 times 2 plus 0 times 7. And that is the matrix product. And we're starting with a 2 by 2. We're multiplying it by 2 by 3. We can form the product because the inner numbers match. That's what we needed. And then the resulting matrix will have the outer numbers as its dimensions. We get a 2 by 3. Now, of course, nobody would leave it like this. 1 times -1 plus 3 times 0 is -1. 1 times 5 plus 3 times 4 is 5 plus 12 is 17. 1 times 2 plus 3 times 7 is 2 plus 21 is 20. 2 plus 21 is 23. -1 times -1 plus 0 times 0 is +1. -1 times 5 plus 0 times 4 is -5. And -1 times 2 plus 0 times 7 is -2. So this is the resulting matrix. And I know that this is a complicated operation, but there is a very good reason why it's defined this way. It has to do with function composition. Without spoiling too much for you, this is the necessary way to define matrix multiplication so that you can divide matrices and get solutions to matrix equations, aka linear systems. Okay. I would like to do one more example here where we're multiplying some matrices just for fun. And I want to take two matrices that are the same size so that I can form the product in either direction. So let's let A be the 2 by 2 matrix, 5, 7, -3, 0. And let's let B be also a 2 by 2 matrix, 1, 2, 9, -1. And I want to form both products, AB and BA. Since these are both 2 by 2s, I can actually form both products. I can multiply in either order. What you're going to see, though, may surprise you. AB is 5, 7, -3, 0 times 1, 2, 9, -1. It's going to be another 2 by 2. Whose entries are 5 times 1 plus 5 times 1 plus 7 times 9. I'll write it out. Then row 1, column 2, 5 times 2 plus 7 times -1. To 1 position is -3 times 1 plus 0 times 9. And the 2, 2 position is -3 times 2 plus 0 times -1. And if we simplify, that's 5 plus 63, right? 5 plus 63 is 68. 10 minus 7 is 3. -3 plus 0 is -3. And -6 plus 0 is -6. So AB is the matrix 68, 3, -3, -6. BA, just swap these around. That's 1, 2, 9, -1 times 5, 7, -3 is 0. Now I take rows of this with columns of this. So that's 1 times 5 plus 2 times -3. Rows here, columns here. So 1 times 7 plus 2 times 0. Row here, column here. 9 times 5 plus -1 times -3. And row here, column here, 9 times 7 plus -1 times 0. I'm just doing the arithmetic now. That's 5 minus 6 is -1. 7 plus 0 is 7. 45 plus 3 is 48. And 63 plus 0 is 63. And what we see is that these are very different. A times B is not the same as B times A. These are totally different matrices. And this means matrix multiplication is not. What's the name of that property like 5 times 6 equals 6 times 5? It's called commutativity. So matrix multiplication is not commutative. In other words, the order you write down the matrix multiplication matters. So when we talk about multiplying two matrices, I can't just say I'm going to multiply the matrices A and B. I have to say I'm going to multiply A times B, or I'm going to multiply B times A. They're not the same thing. Usually we specify, like here I would say, I'm going to multiply the matrix B by the matrix A on the left. And over here I would say, I'm going to multiply the matrix B by the matrix A on the right. You have to specify which side you're multiplying on. And that's a very funny property of matrices. Probably for most of us, this is the first non-commutative operation we've met since division. Right? 3 divided by 5 is not the same as 5 divided by 3. Division is not commutative. But we don't usually think of it that way. It's not something people think about too often. But certainly, matrix multiplication is not commutative. There are some true statements about matrix multiplication, though. It is associative. If A, B, and C are all matrices whose dimensions allow the multiplication, then A times B times C will be the same as A times B times C. So you can't flip the order over, but if you're multiplying a string of 3 matrices, you can either do the first 2, then the third, or the first times the other 2 multiplied first, right? So if I wanted to multiply A times B times C, I could do B times C, and then multiply that on the left by A. And that would be the same as if I formed A times B, and then multiplied that on the right by C. Also, this is distributive, which is really nice. A times B plus C is the same as AB plus AC. That's not obvious, but it is true. And you can distribute not only on the left, but also on the right. So if you had like A plus B times C on the right, that's the same as AC plus BC. This first is called associativity. Matrix multiplication is associative. And these are 2 different flavors of distributive property. Okay. We are right at time here, but I want to spend just one more second explaining to you why this shit is so important. And then next time we will finish up by talking about how to use these matrix multiplication rules to solve systems.
When is our test?
So your last midterm, I'm going to be giving you as a take-home test, and I will hand that out after class on Wednesday. So your last midterm has to do just with these systems and stuff, and I will send that out as a PDF on Wednesday after class. It will be due on the day of your final, and you'll be downloading the PDF, printing it out, writing on that test, then scanning and submitting. So it's not going to be a proctored test the way our other midterms have been. It will be just like a worksheet, a take-home test. I'll give very clear instructions. Okay, so why do we care about this? Why all this crap? Consider the matrix equation (1, -1, 3, 1, 2, -2, 3, -1, 5 times little x, little y, little z as a column equals. You can form this product. This is a 3 by 3. This is a 3 by 1. So the result would be another 3 by 1. And let's imagine that that is 4, 10, 14. If we multiply out the matrices on the left, we get a new matrix, which is a 3 by 1, whose entries would be 1x plus -1y plus 3z. In other words, x minus y plus z in the first entry. 1x plus 2y minus 2z, or x plus 2y minus 2z. And 3x minus 1y plus 5z. And the right-hand side here would still be 4, 10, 14. And this is a 3 by 1. This is also a 3 by 1. So this statement that this 3 by 1 matrix, right, it's just This is one entry, it's just a number. This is one entry, it's just a number. This is one entry, it's just a number. The statement that this 3 by 1 is equal to this 3 by 1 is equivalent to the system. Well, in order for these matrices to be equal, I need this to be equal to this. So x minus y plus z equals 4. I need this to be equal to this. So x plus 2y minus 2z is equal to 10. And I need this to be equal to this. So 3x minus y plus 5z is equal to 14. And what that means is this system is equivalent to this matrix equation, which is equivalent to this matrix equation. So if I wanted to solve this system, I could write this matrix equation and then try to solve this matrix equation. And normally we would say this equation is of the form capital A times capital X equals capital B, where A is the coefficient matrix to this system, and B is the right-hand side. Right, A would be 1, -1, 3, 1, 2, -2, 3, -1, 5, X would be the column of variables, little x, little y, little z, and B would be the column of right-hand sides, 4, 10, 14. So solving a linear system, a system of linear equations, is equivalent to solving the single matrix equation AX equals B, where A is a constant matrix, and B is a constant matrix, and X is a matrix made up of the variables little x, little y, little z. Next time, I will show you how to solve AX equals B. Entirely in matrix land. So rather than doing all that ugly work with the systems, like from your last homework set, rather than row reducing a big matrix, you can set up this matrix equation and solve that. And this turns out to be a pretty cool thing. It requires some concept of division by this matrix, right? Like if I wanted to solve this for x and these were all just numbers, I would divide both sides by a. But we've seen that matrix multiplication is kind of complicated, and matrix division is thus kind of complicated. And we will talk about that next time. They're called matrix inverses. That will be the end of the course for us. So there are a few things that I would like to be able to share with you guys at the end of the term here that we just don't quite have time for. I think I will probably record after Wednesday. I'll record one more little lecture for you that won't be relevant to your take-home exam, but will be stuff that you need to know moving into calculus. Just a little bit of notation on series, sigma notation. I won't beat you up about it on the tests, but I do need to expose you to it. But yeah, that's it. So next time we're going to talk about solving matrix equations of the form AX equals B, and that will be the end of our study of systems. The exam, your final, not final, your last midterm exam, exam 4, is going to be a take-home test. By that, I mean it will be a paper test that I post a PDF to Canvas for you to download and work out. And then you will scan your worked version of that test. And I will ask you to please print the test. Don't just write the stuff on notebook paper. It makes it so much harder to grade. That's it from me for today. I will see you guys on Wednesday. Take care.